Welcome to Understand the Math. In this Calculus 1 video, we're tackling one of the most fundamental ideas in all of calculus, the precise definition of a limit. We'll talk about why we need a precise definition, go through it step by step, and then walk through some examples that show how it works. Be sure to download the free guided notes to help you follow along step by step. Let's start by looking at why we need a precise definition of a limit. I've written down an example of a function f of x that I've graphed over here on the right. We're going to be looking at the limit of our function f of x as x approaches the value 2. The general definition of a limit tells us that the limit of f of x as x approaches a is equal to L if and only if the limit of f of x as x approaches a from the left is equal to L and the limit of f of x as x approaches a from the right is also equal to L. Let's now look back up at our graph. From this definition, we can see that the limit of f of x as x approaches a from the left, that's going along this line, and as x approaches a from the right, that's going along this line, is equal to this value here that we're going to call L. So we can write down that the limit as x goes to 2 of f of x is equal to 8. Our limit definition means that we can make our function's output f of x as close as we want to our limit L by choosing inputs x that are sufficiently close to the value a. We need a precise understanding of what the phrases as close as we want and sufficiently close really mean and how they're connected mathematically. The precise definition of a limit, otherwise known as the Epsilon-Delta definition of a limit, gives us this understanding and forms the foundation for rigorously defining derivatives and integrals. Let's now look at the formal definition, otherwise known as the Epsilon-Delta definition of a limit. This definition tells us that we're going to let f of x be a function defined on an open interval containing a, except possibly at a itself. We can say that the limit of f of x as x approaches a is L if for every number epsilon greater than 0, there exists a number delta also greater than 0, such that if 0 is less than the absolute value of x minus a is less than delta, then the absolute value of f of x minus L is less than epsilon. Let's now make sense of all this. Let's start by getting a better understanding of this expression. 0 is less than the absolute value of x minus a is less than delta. I think it's easier to understand this if we get rid of the absolute value. So let's do that. We can get rid of the absolute value by writing it like this. Minus delta is less than x minus a is less than delta. And then we're going to isolate x. So we're going to add a to all three pieces. And we get a minus delta is less than x is less than a plus delta. Let's hold on to that for a minute, and let's do the same thing for our other inequality. We were given that the absolute value of f of x minus L is less than epsilon. That means minus epsilon is less than f of x minus L is less than epsilon. If we add L to all three pieces, we get L minus epsilon is less than f of x is less than L plus epsilon. These inequalities tell us that f of x is in this interval here when x is in this interval here. Here's how this works in practice. You decide how close you want f of x to get to L. That's your epsilon. Then you determine how close x needs to be to A, that's delta, to make that happen. We're now going to look at some examples to make this definition make a little bit more sense. We're going to look at an example where we're going to find delta for a given epsilon using a graph. We're given the graph of f of x, and we're told that this function satisfies the limit of f of x as x approaches 3 is equal to 6. On our graph, here's 3 and here's 6. We want to find the largest number delta such that in part A, if 0 is less than the absolute value of x minus 3 is less than delta, then the absolute value of f of x minus 6 is going to be less than 2. And this 2 is our epsilon. We're going to do something similar for part B. To find delta in part A, we are going to begin with the then part of the statement. Our then part of this statement says that the absolute value of f of x minus 6 is less than 2. Let's get rid of the absolute value and write this as minus 2 is less than f of x minus 6 is less than 2. Let's add 6 to all three pieces, and we end up with 4 is less than f of x is less than 2 plus 6, which is 8. F of x needs to be between 4, located here on our graph, and 8. We want to find delta so that f of x lies between 4 and 8. Let's go up to our graph and let's see where 4 and 8 lie on our function. We're going to go up to 8 and we're going to draw a straight line over to the graph and mark that point. And then we're going to do the same thing down here at 4 and we'll mark this point. These 2 points correspond to x lying within this pink region. Let's label this so you can see it. This is 3 plus delta, and then this is 3 minus delta. To find delta, we can see that 3 plus delta is approximately 3.6. That's looking at this point right there. Subtracting 3 from both sides, we get that delta is approximately 0.6. This tells us that the largest value delta can be is 0.6 to ensure that our function lies between 4 and 8. And let's just make a note that our epsilon from up here is equal to 2. Now let's look at part B. We're going to do the same thing, but now our interval for f of x is going to be smaller. We have f of x minus 6 is less than 1. So we have minus 1 is less than f of x minus 6 is less than 1. Adding 6 to all three pieces, we get 5 is less than f of x is less than 7. Let's also make a note that epsilon is equal to 1. And let's go back up to our graph and let's put in 7 and 5 because that's what f of x has to range between. Let's now draw a line over to our graph from both of those, and then we're going to draw our line down. Now we have to look at our graph and we're going to have to estimate what 3 plus delta is equal to. Let's put in our graph here that this point is 3 plus delta. So we have 3 plus delta is approximately, that looks like about 3.25. Subtracting 3, we have delta is approximately 0.25. And that's our answer. If delta is 0.25 or smaller, we can ensure that our function, f of x is going to be between 5 and 7. In this example, we are going to prove a limit statement using the epsilon-delta or precise definition of a limit. We're going to prove that the limit of 3x minus 2 as x approaches 2 is equal to 4. Just to make things easier, I've written down some statements that we can follow just to give us some structure. We're going to start with statement 1. It says, given epsilon greater than 0, choose delta equal ... We have to fill in what that ... is, and it is going to be epsilon divided by some number. We are going to use statement 2 to find that number. What actually happens in practice is you start with statement 2 and you find delta. Then you go back and write statement 1, statement 2, and then statement 3 and 4. Let's go through our example so you can see exactly how this works. I am going to start with statement 2, and if we look up here at statement 2, we are going to plug in a, f of x, and L, and our goal is to find delta. If 0 is less than the absolute value of x minus a is what x is going to, and in our example, x is going to 2, so we're going to put a 2 in here, is less than delta, then we have the absolute value of f of x, which is 3x minus 2 in our example, minus L, which is 4. And we have to find out what this is, so let's simplify. This is 3x minus 6. We can pull the 3 out, and we get x minus 2. Now we're going to substitute that the absolute value of x minus 2 is less than delta. So this part is going to be less than delta. So we can say that this is less than 3 delta, and we're going to set that equal to epsilon. So we have epsilon is 3 delta. So we can infer that delta is epsilon divided by 3, which is exactly what we needed. Now that we know what delta is, we can go ahead and write down our proof. I'm not going to list the statements in the proof, but I am using them as a guide. Here we go. We're going to write down given epsilon is greater than 0, we're going to choose delta to be epsilon divided by 3, period. Now we're going to say if 0 is less than the absolute value, x minus 2, plugging in a is 2, is less than delta, then the absolute value of f of x, which is 3x minus 2 minus 4. I know we're repeating what we already did, but you have to do that with the proof, is equal to the absolute value of 3x minus 6 is equal to 3 absolute x minus 2 is less than 3 delta. And we know that delta is epsilon over 3. So we can say this is 3 times epsilon over 3, which is epsilon, period. Now let's look up at statement 3. Starts with a thus. So we're going to write down thus. If 0 is less than the absolute value x minus 2 is less than delta, then the absolute value 3x minus 2 minus 4 is less than epsilon, period. One more. Let's look up at statement 4. Starts with a therefore, so we're going to write down therefore. By the definition of a limit, we can conclude that the limit of 3x minus 2 as x approaches 2 is equal to 4. And that's it. You've seen why we need a precise definition of a limit, how to state it formally, and then how to apply it with both graphs and proofs. To really master this concept, make sure you work through plenty of practice problems on your own. If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.